Alright, hello, welcome to Intro to Mathematics. My name's Nathan Frey, and I'll be your teacher for this course. This course is a basic college-level math to introduce you to concepts from arithmetic, which we're going to start with, and then we get into some geometry, and then a little bit of algebra, and some probability and stats. In this arithmetic part here, we're going to start talking about number systems, our base 10 decimal system, order of operations, PEMDAS, operations with fractions, decimals, percents, and problems using ratios, rates, and proportions. Tonight, we're going to be covering what you're going to need to know for Quiz 1, starting with our number systems. So here is a Venn diagram showing you the sets of numbers and where each one belongs. So the smallest set, when we start talking about numbers, the most natural place to start is with the natural numbers, and these are also sometimes called counting numbers, but for this course we're going to call them natural numbers, and we can abbreviate those with the number n. Natural numbers are the ones that we use for counting, like 1, 2, 3, 4, and so on. So any number that would appear in this list would be a natural number. And if we add the number 0 to it, 0 gives us the whole numbers. Notice that 0 kind of looks like a donut, and donuts have holes, so that's how I remember that. The whole numbers are these natural numbers and the number 0, and we can abbreviate those with the letter W. The whole numbers are great if we just want to add and count things, but if we start losing things or going into debt or having to pay for a pizza, then we'll have to use some integers. So the integers allow us to add and subtract, and we have all the numbers 1, 2, 3, 4, and so on, and their opposites, -1, -2, -3, and so on, and 0. So those are called the integers, and we use the letter Z to represent the set of integers. Next up, we come across the rational numbers, and the root ratio means that to cut something. So rational numbers or ratios are where we take a number and we cut it into pieces. Like take a pizza and you split up the pizza into 8 slices, and you take a slice, that's 1/8 of the pizza. So anything that can be represented as a fraction using integers is a rational number. So we can represent rational numbers such as 2. Any integer is also a rational number, like 2, we can write as 2 over 1, or -3 is a rational number because we can write it as a fraction using integers. And we have fractions like 1/4, 1/2, 3/4, which if we make those into decimals, 1/2 is the same as 0.5, 1/3, if we take 1 divided by 3, 3 doesn't go into 1, so we have to add a decimal, add a 0, and then we can start dividing. And we get a repeating pattern here. So if you have a repeating decimal, 0.3333 and so on, that's going to give us a rational number as well. 0.3 repeating, if we want to, we can write that as 0.3 with a little bar over it. As far as for your quiz, when you do your quiz on Moodle, you can write this as 0.333 ... and the 3 dots afterwards tells me that you know it's repeating. We can also write these numbers as percents, like 30%, 75%, and so on. And then, on top of that, or opposed to the rational numbers, we have the irrational numbers. So you're either rational or you're irrational. Irrational numbers cannot be written as a fraction using integers, so cannot be written as a fraction. Using the integers, so there's no way I can write like the square root of 2 as a fraction using these guys here on the left side. The same goes for pi. Pi is the number that we use for calculations with circles. It starts out with 3.14, 15, 926, and so on, but it goes on forever. These irrational numbers have decimals that do not stop or terminate, so they don't terminate. They don't terminate or stop, and they don't repeat. So we can't just put a bar over it like we can for 0.3 repeating. and they don't repeat. And then including all these numbers, the rationals and the irrationals, we have the real numbers. Now, you have to keep in mind that this Venn diagram is like a set of nesting dolls, like the Russian dolls, where one doll is inside of another doll, which is inside another doll. So, for example, 2, we saw over here, 2 is a rational number because we can write it as a fraction. 2 is also an integer because it's going to be in this list of integers. 2 is a whole number, and 2 is a natural number. So it's possible, and 2 of course is a real number too, because all of these are going to be real numbers. So it's possible for a number to be in more than one set. So the first thing you're going to do is to list out all the sets to which these belong. Here are some examples. I'll go through the ones here on the left side, and if you want to look at this PowerPoint, you can do the ones on the right side for practice. So 11/8, this is a fraction, so that means it's going to start with a rational. It's not an integer, so it's not a natural number, it's not a whole number. I wouldn't see it on those lists, but it's definitely a fraction. And it is also a real number, so I use R for real. 12, on the other hand, what is 12? Well, the first place I start to see 12 is it's a counting number. I can count up to it. Since it's a counting number, it's also a whole number. That means it's also an integer, so I'll put a Z for integer. And it is a rational number, because I can write it as a fraction, 12 over 1. And then it's also a real number, so I put an R there. So 12 is almost all of them. It's not irrational. So if you're rational, you're not irrational, and vice versa. Irrational, you're not going to be rational. 0, where do I first see 0 on the list? Well, that's going to be a whole number, and it's an integer. And it is a rational number, because I can write it as a fraction, 0 over 1, and then it's a real number. Square root of 20, well, square root of 20, if you put it in a calculator, you come out with a decimal. It doesn't come out evenly, as opposed to like if it was square root of 25, then that could just be simplified to 5, and that would be rational. But square root of 20 is irrational, and there's no strict symbol for that. I can abbreviate that with IRAT like this, so I don't have to spell out the whole thing. And its irrational numbers are also real numbers, so I'll put an R for that. What about 13/7? What do you think that would be? Well, if you said rational, you are correct. So that is a rational, and that is a real. We'll do one more here. What about -12? Well, it looks like 12, except -12 is not a counting number, so the first place you would see -12 would be the integers. And then, of course, it's a rational number, and it is a real number. So hopefully that gives you enough practice, enough sample, example questions here to get an idea of how to do this. If you have any questions, just let me know. The next thing we're going to go over is our decimal system. Deci means 10. So think about, the months in a year. So we have, October. Oct means originally 8. November. Nov or non means 9. And then after that we have December. Des means 10. Originally the calendar had these as its 8th month, 9th month, and 10th month until July and August were added. So we still have these prefixes, and even September has the prefix for 7 there. So deci means base 10, and the reason I think we came up with the base 10 is, well, it's right on the fingers. Right? You got 10 fingers, so imagine cave peoples just start counting 1, 2, 3, 4, and then they keep track. Oh, there I got a group of 10, and then they count up to 10 again. They got another group of 10. If they use their fingers and their toes, we might have a base 20 system. Who knows? Not all societies had a base 10. Some had base 60, where we get 60 seconds in a minute, and 60 minutes in an hour, and so on, and 360 degrees. The Babylonians had a base 60, but for most part we use base 10. And that means that as you go to the left, every time you go to the left, it's going to be 10 times as much. So we have the units or the ones place, sometimes we say rounding to the nearest whole number, so these are all whole numbers. And then if we go to the left, that's 10 times as much, that's the tens place. You go to the left again, we've got the hundreds place, and then the thousands place, 10,000, 100,000, until we get to million. And the pattern kind of starts repeating. We got 10 million, 100 million, and then we got billion. So just if you want to get to really big numbers, million, billion, starts with a B-I. Bi means 2. Then we've got trillion, which has to do with 3. After that is quadrillion. Quad has to do with 4. We're not going to go up quite this high, so as long as you know up to a million, that's probably enough. But, you know, in real life you hear about billions and trillions sometimes when you're talking about billionaires and debts and things like that. So here is the decimal system, and notice that when you go to the left, or to the right one spot, we are dividing by 10. So, you know, here was the 1 spot. Divide that by 10, we've got the 10th spot. Divide that by 10 again, we've got the 100th spot. Go to the right one more time, we've got the thousandths spot. 10,000ths. Notice that each of these is going to end in a TH to tell us that we're getting smaller and smaller. And then the 100,000ths. So when you go to the left, you multiply by 10, and when you go to the right, you're dividing by 10. Notice that there is no oneths spot. It wouldn't really make sense because 1 over 1 is the same as 1. So when we go to the right after the decimal place, it starts with the tenths and not the one spot. And so we're going to be using this to estimate and round our answers. So here's some examples where we have to name the decimal place, and then we're going to use this to round. So like the 2 here, that would be in the 10 spot. So as we go across here, we've got the ones, the tens, the hundreds, the thousands. The 2 that's underlined is in the 10 spot. For number 3, this 9, which decimal place is that in? Well, the 8 is in the 1 spot, and we go to the right, we've got the tenths, the hundreds. Remember, we start with tenths, hundreds, and thousands. So this would be the thousands place. And for number 5, we got a 1, and then this is a decimal. You got to be careful with the decimals and the commas. So when we go to the right, this first decimal place is going to be the 10th spot. And for number 7, we have a comma here. And here is our decimal place. So the 5 is in the 1 spot, and the 4 would be in the tens spot. Notice the difference between tenths and tens. If I keep going with this, so we got the tens, and then the 5 would be in the hundreds, the 1 would be in the thousandths, the 0 is in the 10,000ths, and the 3 would be in the 100,000ths place. Also with commas and decimals, here in the United States, we use decimals for the decimal place to show smaller numbers, and we use the comma to set off groups of 3. Now, if you go to England or other British-speaking countries, they sometimes do it backwards. They'll use a comma for a decimal and a decimal for a comma. So if you're from a different country, it might be a little bit confusing. So make sure that that is clear. And here for number 9, what do we have here? Let's start here at the 8. We got the ones, tens, hundreds, thousandths. And the commas here make it easy because now we know that, okay, we got a comma here, that's the thousands. We got a comma here, that's the millions. So this would be the 10 millions spot. We'll do one more here. Look at number 4, because now we go in the opposite way here. So here as a decimal place, the 4 is in the 1 spot. The 6 would be in the tenths. And then we've got the hundredths, the thousandths, the 10,000ths, and it looks like the 4 there is in the 100,000ths spot. Okay. And on the slideshow, you can see the answers to the other ones if you were working those out. Now we're going to do some rounding. So For rounding, here's what we're going to do. So it tells us to round to a particular value. And for me, first off, when I'm rounding, I think, okay, 100,000, that means, like, imagine I just have 100,000 bills and I have to come up with this amount of money. How many bills would I have to give in order to be close enough to this number? And all I have is 100,000 bills. I can't break it up any smaller. So we want to get as close as we can to the given number if we have only 100,000 bills. And here are the steps for rounding. So first step one is I like to underline the name, the place value. So we're going to underline the place value that we're talking about, that we want to round to. So underline the place value. And then we go to step two. Step two, we're going to look to its neighbor, to the right. So look to the right. Look to the right. And we have to make a decision. So here's how we make our decision. If the number to the right is 4 or below, then we round down. And let me explain what round down means. So round down means that the underlying number stays the same. So the underlying number stays the same. And then we replace everything to the right with zeros. So replace everything to the right with zeros. So step one, underline the place value. Step two, look at the number to the right. And if the number to the right is 4 or below, then we're going to round down. By rounding down, we're going to underline that number. The underlying number is going to stay the same, and everything to the right is going to become a 0. And then the other option is if the number to the right is 5 or greater. So 5 or greater. 5 or greater, then we're going to round up. So we're going to round up. And if we round up, the underlying number it goes up by 1. And then again, everything to the right becomes zeros. So zeros to the right. Everything in front of that number would stay the same. All right, so let's see how that would work here. So let me change colors here. So imagine we're doing for number 1 here. It says to round to the nearest 100,000th place. So the first thing we're going to do is to find a 100,000th place. So 3 here is in the 100,000th place. That's the number we're rounding to. And then we look to the neighbor to the right. It's an 8. Okay, 8 is big. It's bigger than 5. So if it's 5 or bigger, we round up. So that means that the 3 is going to round up to a 4. And all the numbers to the right are going to become zeros. And everything to the left is going to stay the same. So we get 62,400,000. And notice when I read it, I end up with 100,000. That's the last thing that I read. There's no other, digits and any other place value after 100,000s. So 100,000s is what I rounded it to. Number 3, here's some decimals. So decimals, the same rules are going to apply. So here we're going to round to the thousandths place. So we got the tenths, the hundredths, the thousandths. Looks like the 3 is in the thousandths place. And so we look to the neighbor, and that's a 4. So that means that the 3 is going to stay the same. Everything in front of the 3 will stay the same. Everything behind the 3 will become a 0. So the 4 will become a 0, the 2 will become a 0, and the 6 will become a 0. So we can write it as 4.063000. Now, in this case, since these zeros are to the right of a decimal place, we call these trailing zeros, and they don't really add any extra value to our number. We can just take them off, and we could write this as 4.063. So either way that you write it, that would be correct. So there is our number rounded to the nearest thousands. And the correct way to read this would be 4 and 63 thousandths. That's the correct way to read it. I know usually I read it as 4.063 because that's easier to read it that way. But technically we should read it as 4 and 63 thousandths. And we know that we've rounded to the thousandths because that's the way we read it. For number 5, we're going to round to the nearest hundred thousandths. So we got to find the hundred thousandths place. So again, we've got the tenths, the hundredths, the thousandths, the 10 thousandths, and the 100 thousandths. So now when we look to the right, it's a 5. So this one has to be rounded up to 9. And that means that the next number is going to be a 0. And everything in front will stay the same. And so we can write it as 7.56159. And this one, if we're reading it technically, this one's a little bit harder to read. It would read as 7 and 56,159 hundred thousandths. So that's why I usually just say 7.56159. And there we have it rounded. Okay, number 7, hundredths. This is like rounding to the nearest penny. Okay, if we're talking about money. So if I round to the nearest penny, this would be 1.94. Because the 4 was in the hundredth spot. The next number over is a 3. And so we're going to round it down, and we'd have $1.94. $1.94 or $1 and 94 hundredths. If it says to round to the nearest ones place, that's rounding to the nearest whole number. So we don't want any decimals for that one. So here is the 1 spot, and to the right we got a 3. So again, we're going to round down. And so everything to the left is going to stay the same. The 2 is going to stay the same. Everything to the right would be a 0, and we'd have 43,552. Here are the answers to the remaining problems. Okay, the next thing I want to go over is order of operations. PEMDAS is how you might have heard this before. Or please excuse my dear Aunt Sally. And PEMDAS stands for parentheses, exponents, multiplication and division, as you go left to right, and addition and subtraction, again, as you go left to right. And a couple things to clarify here is, first off, these are like stair steps. And the first stair step is for the P, that is the parentheses. And the parentheses includes any grouping symbol, including parentheses, brackets, fraction bars, absolute value. The absolute value we're going to talk about is these little bars right here. So just as we're on this absolute value is the distance from 0. So absolute value acts kind of like a grouping symbol, and if you got something inside of it like 2 minus 6, and then you got some stuff on the outside like plus 8, well, you got to do the absolute value thing first. So 2 minus 6 is negative 4, so you do what's inside of it. Then you take the absolute value. So what is the absolute value of negative 4? Well, that means how far is negative 4 from 0 on the number line. So 1, 2, 3, 4, there's negative 4, and it is 1, 2, 3, 4 away from 0. So the absolute value of negative 4 is positive 4. So we get 4 plus 8 for a final answer of 12. So again, absolute value means the distance from 0. It's always going to be non-negative. So if it comes out to a negative number inside of it, we make it positive. And if it's 0 inside, it's just going to be 0. And we got to do that first, and then we do the absolute value, and then we can do the things on the outside of it. So parentheses and grouping symbols come first, and then we do exponents. And for exponents, you have to do, along with exponents like squaring, like 5 squared would be 5 times 5, or 25. We also have to do square roots, like the square root of 25 is 5. Or another example of exponents and roots, 2 cubed would be 2 times 2 times 2, which is 8. And so the cube root of 8 is the opposite of that, is 2. You should be familiar with these operations and where to find them on your calculator or on Desmos. And I'll be pulling up Desmos to show you where you can find some of these operations. So exponents come second, and then we get to the third step. And the third step is kind of misleading because we read this as M and then D, but the M and the D happen at the same time. We do multiplication and division at the same time as you go left to right. So, for example, if I had a problem like 6 divided by 3, and then times 2, for example, this is how we do it. Even though the M comes before the D, they happen at the same time as you go left to right. So as I go left to right, what do I come across first? I come across 6 divided by 3, so that's what I resolve. 6 divided by 3 is 2. Then I would have 2 times 2 is 4. So you can see that the order that I do them in matters. If I do 3 times 2 first, then I would get a completely different answer. Now your calculator and online calculators and so on will do this automatically. So if you just type it in like this, they'll automatically know what order to do them in. Now, if I wanted to do the 3 and the 2 first, then I should put parentheses around it. So, if I had parentheses around the 3 and the 2, well, that's a different thing. Then I'm starting off with the parentheses, and I would have 3 times 2, that would be 6, and 6 divided by 6 is 1. So again, the order matters. If there's no parentheses and you have multiplication and division, you do them as you come across them, reading left to right. The same goes for addition and subtraction, and the reason is that addition and subtraction are basically the same operation. The same, multiplication and division are really the same operation, so they happen at the same time. So addition and subtraction, again, if I had 6 minus 4 plus 2, then I would do 6 minus 4 is 2, 2 plus 2 is 4, something like that. And while I'm talking about subtraction, you should be careful with subtraction and negative numbers. So, for example, if I have something like 2 minus 8, you could always change subtraction to adding the opposite. So 2 minus 8 you could write as 2 plus a negative 8. Either way you write it, you get negative 6. So subtraction you can write as adding the opposite. And this means, I would start here at 2, and then if I'm going negative 8, that means I'm going backwards 8 spots, and I would end up at negative 6. So if I add a negative, that means going to the left. If I subtract a positive, that also means going to the left. And if I do something like 2 minus a negative, so here we have 2 minus a negative 8. The same thing applies. When you have a double negative like this, you can change the subtraction to adding the opposite. And what is the opposite of negative 8? It is positive 8. 2 negatives like this will become a positive. So 2 minus a negative 8, it means you're switching directions, and then you switch again, and you end up going in the positive direction. You end up with 10. So those are the basic order of operations. Let's look at some examples of those. So here's a few that I want to look at. So for number 1, notice you have subtraction, you have division. What's going to come first? Well, of course, the division is going to come first. PEMDAS, please excuse my dear Aunt Sally. Parentheses, exponents, multiplication, division, addition and subtraction. So the division comes before the subtraction. 3 divided by 3 is 1, and then 6 minus 1 gives you 5. For number 3, 2 plus 4, that's in parentheses. And here we're using the little x to mean multiplication, although that can change. There's many ways of writing multiplication. But let's just finish this problem here first. 6, we're going to do the parentheses first, times 2. That's going to give us 12. What's another way you could write 6 times 2? Well, you might see a little dot. So if you see a dot like that, that also means to multiply. Or maybe one number or both numbers are in parentheses. That also means to multiply. And the last example might be if you have a variable like 6x. And if x equals 2, then 6x is also equal to 12. So we're going to try to get away eventually with this little x for multiplication and start using a dot or using parentheses most of the time. But here at the beginning of this course, when you do see a little x like that, it will mean multiplication. Usually if I want a variable, I will write it in script like this. So you'll be able to tell the letter x apart from the symbol for multiplication. For number 5, here's where we have a fraction bar to show you how that can be used as a grouping symbol. When you have a fraction bar, you have to resolve what's on the top and resolve what's on the bottom before you do the fraction, before you divide them. So on the top, 1 minus 4, that gives you negative 3. And on the bottom, notice that you have parentheses here around the negative 1. You might think, oh, parentheses, I got to do something with that. But here, the parentheses are just telling you that, watch out, you got a negative number. So sometimes parentheses just mean there's a negative. You got to be careful. You're coming across a negative. So in this case, you can drop the parentheses. They're not really telling you to do anything inside. They just say, watch out, there's a negative. And we have negative 1 minus 2, and that's going to give us a negative 3. Now that I have the top and I have the bottom, now I can do the fraction bar, which tells me to divide the top by the bottom. And so a negative divided by negative is going to give us a positive 1. In this course, unless said otherwise, you should always reduce fractions into lowest terms. So make sure you simplify all your answers. Make sure you simplify all your fractions, unless I say, not to simplify it, or if you're making some kind of equivalent fraction or something. For number 7, here's a good example where we have the parentheses telling us here to multiply, and we can see we're subtracting a negative. So we could rewrite this without the parentheses, just to make it a little bit clearer. So we have 4 minus 4. I'll change that to a dot. Here I have parentheses, but that one is just saying you got a negative. And now I have subtraction and multiplication and more subtraction. So you would do the multiplication here first. And then here it's subtracting a negative, so that's going to become a positive. And now we have addition and subtraction, which we can just resolve going left to right. So make sure you go in this order. 4 minus 16 is going to be negative 12. Negative 12 plus 5, the negative is going to beat out the positive number, so we're going to end up with a negative 7. A couple more examples here, just to show you this one's got an exponent. So we do the inside the parentheses. 10 divided by 5 is 2. 5 squared. Again, squaring means multiply by itself, so we end up with 25. And number 6, here's an example of what I was saying with the absolute value bars. So these bars right here, these vertical bars, are saying to take the absolute value of whatever's inside. Now, you do not just make everything positive inside. Some people might think that. It's not going to change anything on the outside. So these parentheses are just saying you have a negative number. We're subtracting negative 5 minus 6. And before we do anything with the absolute value, we have to simplify the inside of that down to a single number. So negative 5 minus 6 gives us negative 11. Then we can take the absolute value. And when we take the absolute value, it's not going to affect anything on the outside, so it doesn't change this minus sign. It only changes what's inside here. Since it's the absolute value of a negative, it's going to become a positive 11. 5 minus 11 gives you negative 6. I want to show you the websites that we're going to be using, Desmos, and make sure that you see these operations on there. So Give me a moment to change over. Alright, so here we are on the Desmos site, and again, this is a free calculator that's available online, or you can download it as an app. If you download the app, make sure you get the graphing calculator version. So here's where you're going to type your things in. Here's where it shows the graph. It will graph things and would also do all the normal operations. So like here is absolute value. If I type something in, I can always move with the arrow keys. So let's say I had 5 minus, I forget what the problem said. I think it said -5 minus 6. Okay, and it will automatically put the absolute value bar at the end. And you can see it's doing the same calculation. So there's absolute value. Here's where you can square something. So if you go back up here, if you have like 3 and you want to raise it to a power, like 3 cubed, there's 3 cubed, so you can use this button for a power. And if you go under here, under functions, and you go all the way to the bottom, you can find the cube root key as well. So let's just do a cube root. Type in a little 3 there, and we'll type in an 8. We see that the cube root of 8 is 2. Also, when you type in a slash, it'll automatically make it into a fraction bar. So you can easily type in your problems like this. Alright, so now we're going to go over how to evaluate expressions. And evaluating is pretty easy. It just means that we're going to plug in certain values in for letters. So these letters are variables and they're going to stand for a particular number. And the problems are going to tell us what numbers to plug in. So for example, number 1, we have 2 plus 4x minus y. When I'm doing these problems, I like to copy it over, take out the variable, put a little parentheses there, take out the y, put a little parentheses there. And then I imagine, okay, so what's going to go in this spot? Well, we're told that x is 4, so we can write that in. And over here, we have y is equal to -2. We're going to put that in. And then after we do that, we can either type this in the calculator, or you should be able to do some of these just by hand. 4 times 4 is 16. We do the order of operations. Here, we're subtracting a negative. 2 plus 16 plus 2 more should come out to 20. When you have 2 letters, 2 variables right next to each other, remember that means that they are being multiplied. So again, I'm going to take out the variable, put a parenthesis, take out the p, put another parenthesis, and we got p is 3, that's going to go in this spot. Q is -5, that's going to go in this spot. And then we want to do order of operations again. So we get -15, 6 plus -15 plus 6. What does that come out to? That comes out to -3. So 6 minus 15 is -9. -9 plus 6 is -3. So you can check that that's what we get there. Number 5, I'll put a little star by. So these ones can be a little bit tricky when you have an exponent. And to show you why, I'm going to change this from the slide to make this a -3. So I want to use m as -3 and p as -5. Now, if you listen to what I said, you will get this correct, because if you take out the m, put a parenthesis, then we're going to square that, and then we've got p, which is -5 minus 3, and for m, we're going to put in -3. If you type this into the calculator or into Desmos, just like this, with the parentheses, you will get the correct answer. Because when you square this, you should be getting -3 times -3, which is 9, plus -5 minus 3 should come out to a 1. Now, however, if you don't and you type this in the calculator without thinking, you could end up with the wrong answer. Because if you type it in like this, the calculator is going to say 3 squared and then take the opposite. So it's going to think that's -9 minus 5 minus 3, and you're going to get -17. So hopefully you did not make that mistake. That would be quite bad. So this is not what we want. That's the bad way to do it. We want to do it the good way, and always put parentheses where the variable is. It's always better to have more parentheses than what you think you need. And we'll look at one more here. Let's take a look at number 6, because again, we got the absolute value there, so I want to make sure you know what that means. This is the absolute value of A, so take out the A, put a little parentheses there. Here I've got more parentheses, and like I said, it's always good to have more parentheses than not enough. -2 is going to go in there. 4 is going to go in here. And then if you realize I don't need all these parentheses, then you can get rid of them. And the parentheses here, I could probably get rid of those too. I still need the absolute value. So what is this telling me? I got to do what's inside here first. 4 plus 4, that's 8. But that is going to be multiplied by the absolute value of -2. So now what is the absolute value of -2? Well, that's going to be +2. And if I've got a number here, notice that there's no operation between the A, or the absolute value of A, and the parentheses. So if you don't see an operation there, like up here, that implies that there's multiplication going on. So we got -2, absolute value of that becomes 2. 2 times 8 gives us 16. So 16 would be our final answer here. Okay, decimals I don't spend too much time on, but just to remind you, when you are adding or subtracting decimals, make sure that you line them up. So for example, if I have 3.2 and I want to add up 5.162, I got to add up the decimal places so they're in the same column. And then you can add on some zeros if you need to, so that everything lines up. And if we're adding, we just just add normal. Okay, and the same is going to go for subtraction. I'll do a quick note here on multiplication and dividing. So when you are multiplying, like 0.8 times 0.4, what you're going to do is pretend that there are no decimals and multiply as usual. So 8 times 4 is 32. Then you see how many decimal places you have. So here I have, 1 decimal place. Here I have another decimal place. So I have a total of 2 decimal places. And so my answer is going to need 2 decimal places. So the decimal place is going to go right there, 0.32. When we're dividing, kind of the same thing. So if I want to take, for example, 0.6 and divide it by 0.1, I'm going to set up this. And usually we don't want a decimal here, so I'm going to move it over 1 spot. And if I have to move this over any places, then I move the outside decimal the same amount. So since I'm moving 1 place to the right, this decimal place is going to go 1 place to the right. And so it's the same as taking 6 divided by 1, which is just going to be 6. So this should come out to 6. If you need more practice with decimals, you can check out Khan Academy. Here are some divisibility rules. And I don't expect that you memorize these, but they will make some of your calculations a lot easier. And I give some examples here in this PowerPoint and in the textbook. So just, you know a number is divisible by 2 if it's even. A number is divisible by 3 if you add up all the digits, like 1 plus 1 plus 1. If you add those all up, you get 3. So here we're looking at the last 2 digits, then you know it's divisible by 4. Here for 5, if the last number is a 0 or 5. For 6, it has to follow the rules for 2 and 3. For 8, you look at the last 3 digits and see if it's divisible by 8. The last thing we have to go over are factors and multiples. So a factor is when we take a number and we are going to break it up into smaller numbers. So they're the building blocks of numbers. So for example, the factors of 12 are all the numbers that divide into 12. So what goes into 12? Well, I think it helps if you list them out in pairs. So like 1 times 12 gives you 12. Then you check the next number. Oh, 2 goes into it. 2 and 6. And then what's the next number that divides into 12? That would be 3 and 4. And you can see if they're paired off that way, it makes it really easy because now you got to the middle here and there's no numbers to check between 3 and 4. And every number is paired off, so you know you don't have to look any further. You've got all the factors at that point. So you're kind of coming at it from both ends, and when you meet in the middle, you know that you're done. So those are all the factors of 12. They're, again, going to be 12 or smaller. They're the building blocks of 12. When we say multiples, that means we're going to count by that number. Or numbers that are divisible by 2. Multiples of 2 would be counted by 2's. In this case, it would be the even numbers 2, 4, 6, 8, 10, and so on. Here, the number of multiples is going to be infinite. So as soon as you establish the pattern, you know what the multiples are going to look like. And we're going to use this to find what's called the greatest common factors and the least common multiple. So for example, we're going to find the greatest common factor of 12 and 18. And then I'm going to do this 2 different ways. So the first way is probably the way that you've learned it back in elementary school. And then I'm going to show you a way that's going to allow you to find it for bigger numbers and to find the GCF and the LCM at the same time. So first off, method 1, the old school method. So when you're first learning about GCF, you probably learned, okay, we're just going to list out the factors. This is the way I learned it. So we're going to list out the factors like I do and pair them off. So we got 1 and 12. Then we have 2 and 6 and 3 and 4. And again, we're coming at it from both ways. So when we meet in the middle, we know we've got them all. We do the same for 18. Pair them off, 1 and 18, 2 and 9, 3 works, 3 and 6. 4 doesn't go into it, 5 doesn't go into it, so we're done. And now you should see some numbers that are common to both lists, like 1 is always on the list. In this case, 2 is also on the list, and so is 3. And if 1 and 2 and 3 are, then 6 is also on this list. We want a common factor, but we want the greatest or the biggest common factor. So what is the GCF of 12 and 18? Well, the GCF of 12 and 18 is the greatest one that's in both lists. In this case, it would be 6. So that's how you do GCF, at least by this first method. Finding the least common multiple of LCM, or the LCM of 4 and 6. So here, again, old school way is to make a list. So we're going to start by counting by 4s. 4, 8, 12, add 4, 16. 4 times 5 is 20. 4 times 6, 24. What's next? 28. 32, 36, 40. That's probably enough. All right, if we need to, we'll go back and add more. 6. 6 times 1 is 6. Times 2 times 3. 6 times 4 is 24. 6 times 5 is 30. 6 times 6 is 36. Then we got 42. Okay, and again, you should start to see that there are going to be numbers that are on both lists. In this case, we've got 36, that's in both. And we've got a 24, that's in both lists. And 12 is in both lists. And it looks like that's it. Okay, so again, and if we keep going, we would have more numbers here that would be in both lists. So we could expand. Remember, both of these lists are infinite, so there would be more and more as we go along here that would be in both. But the least, the smallest in this case, the LCM of 4 and 6 is going to be 12. And so that's the old school way of finding the greatest common factor in the GCF. Now I'm going to show you a new way of doing it, and this is going to allow you to find it for bigger numbers, so you don't have to make these lists. And it's going to find both of them at the same time. So to do this, what we're going to do is to draw a Venn diagram. Venn diagram is just going to be these two circles that intersect each other. The middle part's going to represent what they have in common, and then we have two sections, a section over here on the left and a section here on the right. So first thing we want to do is to find the prime factors of 60 and the prime factors of 42. So if we start factoring this out, I like to divide by the smallest prime first. Primes primes are going to be numbers that have exactly two factors. So primes are numbers with exactly two factors. So for example, one's not a prime because the only factors of 1 are 1. The primes would be like 2 and 3, 5, 7, not 9, because 9 is 3 times 3 and 1 times 9, and then so 11 would be next, 13, then we go up to 17, 18's not, 19 works, 21 is not, 23 I think does. The list of primes is infinite, so all the primes have only two building blocks, two factors, 1 and themselves. So we start with 60 and divide by the smallest, divided by 2, that gives us 30. I keep dividing by 2 until I can't divide by 2 anymore, then let's try 3. Okay, 3 works here. And then if you get down to 1, well, you know you're done. So once you got all primes here, you have the prime factors for 60. It's 2 times 2 times 3 times 5. You do the same for 42. You're going to break it down into its primes. So it's 2 and 21, and then it's 3 and 7. So 42 is 2 times 3 times 7. Now we go to our Venn diagram. So this circle here is going to represent the factors for 60, and this circle here is going to represent the factors for 42. What's in the middle is what they have in common. So when you look at the list that we made, 2 times 2 times 3 times 5, and 2 times 3 times 7, what do they have in common? So they have a 2 in common, so we put a 2 here in the middle. And they also have a 3 in common, so we put a 3 in the middle. And those are all the common factors. Now, we go over here and we say, okay, we've got a 2 left over, we've got a 5 left over, we put those there. And if we go to this side, we've got a, we've got a 7 left over. Put that on this side. And so now, this Venn diagram is going to tell us the least common multiple and the GCF. So the greatest common factor is what they have in the middle. So the GCF is the intersection. The GCF of 60 and 42 is going to be, if I multiply the factors that I put in the middle, 2 times 3, I get 6. 6 is going to be the GCF. The LCM is going to be all these factors multiplied together. So the LCM of 60 and 42 is going to be 2 times 5 times 2 times 3 times 7, which is going to come out to 420. So now I have both the GCF and the LCM pretty simply done. I didn't have to make out a bunch of lists like I did using the old school method. Now you might be like, well, what if I can't write something in one of these circles? Well, you can always write something. So if there's no factors left or there's no factors in common, you could always put a 1 in that spot. And you're going to do the same thing. So the GCF is going to be what they have in the middle. The power of this is that it will work even for 3 numbers. So even if you have 3 numbers, you can do the same thing, except you make a Venn diagram with 3 parts to it. So I'll do one example here. So imagine I'm doing it for 11 and 30 and 36. So 11 is already prime, so I really can't do anything with that. 30 is 2 times 15, which is 3 times 5. And 36 is 2 and 18, and 2 and 9, and 3 and 3. Okay, so in the middle, what do they have in common? Well, they don't have anything in common, so I'm going to put a 1 there. So again, if there's nothing that you can put there, you can always put a 1. Now I look at 30 and 36. So they have a 2 in common, so I put a 2 over there. They have a 3 in common, so I could put a 3 there. And that's it. Here, 11 and 30, they don't have anything in common, so I put a 1. 11 and 36, they don't have anything in common. Then the 11 is going to go here. And the 30 still needs a 5 with it. And the 36 still needs a 2 and a 3. Okay, so from this Venn diagram, I can tell that the GCF of 11, 30, and 36, the GCF would just be 1, because that's the only thing that's in the middle of everything. And it has to be the complete intersection of all 3. The LCM, I would just have to multiply all these out. So I've got 11 times 2 times 3 times 2 times 3 times 5. And you could pick the order, so 2 times 5 is 10. And maybe I do, which I do next. 2 times 3 is 6. 6 times 11, that's 66. 66 times 3 times 10. What does that come out to? Let me grab my calculator quick. 1980 looks like. So 1980. So the LCM is the product of all those factors, the whole union of all of them. So that's 1980. And this should cover the material that you need for quiz 1.